Welcome back, my dear children, for today's class. Today, we will be discussing a topic, PN junction diode. Last class, we have learned the formation of PN junction. A PN junction diode is nothing but a PN junction only, but we have to provide terminals or metal contacts at the ends of the PN junction. So what is a PN junction diode? It is a PN junction. It is provided with the metal contacts or terminals at the ends. This is known as a PN junction diode. A diode basically conducts in one direction. So a PN junction diode, see, you know a PN junction, it has P section and the N section. P section, N section, other side. P section, majority carriers, you know, holes. N section, majority carriers are electrons. And at the center near the junction, there is a thin layer called a depletion layer. Depletion region. Here, near the P section, at the junction, a layer of negative charge. This is called a space charge region. We have discussed it already. Similarly, at the N section, there is a layer of holes, positively charged. These are called space charge regions. This region together is known as depletion layer. And depletion layer do not contain mobile charge carriers. These are the ionized cores. This is PN junction. Now we have to provide metal terminals, metal contacts at the ends. Then we will get a PN junction diode. This is PN junction diode. It conducts only in one direction. The circuit symbol of a PN junction diode is like this. You have to draw a triangle. At the narrow end of the triangle, you have to put a line. This wide end of the triangle represents P section. The line represents N section. So this is the symbol for a PN junction diode. So, dear children, what is a PN junction diode? It is basically a PN junction with the metal terminals or metallic contacts provided at its ends. It will conduct only in one direction. And we know what is depletion region and a potential barrier. At the junction, at the PN junction, there is a potential difference that opposes the further diffusion of electrons and holes, that opposes the diffusion. And at equilibrium, the potential barrier is for silicon diode 0.7 volt, 0.6 to 0.7 volt. For germanium, 0.3 to 0.4 volt. This all we discussed last class. And you know, when the PN junction is formed, when the equilibrium is reached, there is a potential difference here at the junction. This potential difference, it is equivalent to an imaginary, it behaves, it is equivalent to an imaginary battery connected there. This is the battery. This is potential barrier. So when the PN junction is formed at equilibrium, there is no net current across the junction. Now to start conduction, we have to apply an external voltage across the diode. This process is known as biasing of the diode. Biasing of the diode. PN junction diode. So diode, when the PN junction is formed in equilibrium, it is not conducting because of the development of the potential barrier at the junction. So for the diode to conduct, we have to apply an external voltage to overcome the potential barrier. This process of applying suitable potential difference across the diode is known as biasing. So children, what is biasing? Applying suitable potential difference across the diode is called biasing. Across the diode is called biasing. So why biasing is needed? At the equilibrium, when the PN junction is formed, it will not conduct because of the development of the potential barrier. We have to overcome the potential barrier. That is why we have to apply an external voltage across the junction. This process is called biasing of PN junction diode. Now children, there are two types of biasing. First type is called forward biasing. Second type is called reverse biasing. Two types of biasing. Forward biasing. Second is reverse biasing. Now, what is this forward biasing? In forward biasing, the P section of the diode we connect to the positive terminal of the battery, and N section we connect to the negative terminal of the battery. So we take a battery, connect positive terminal to the P section and negative terminal to the N section. It is called forward biasing. Or we can say the P section must be kept at a higher potential compared to the N section. In forward biasing, How we will connect the how we will apply external voltage? P section is connected to the positive terminal. Connected to positive terminal. And N section to negative terminal. Of the battery. And reverse biasing. Here P section is connected to the negative terminal and N section to the positive terminal of the battery. P section is connected to the negative terminal and N section to the positive terminal of the battery. These are the two types of biasing. So in forward biasing, what we will do, P section of the diode is connected to the positive terminal and N section is connected to the negative terminal of the battery. P section must be at a higher potential with respect to the N section. Reverse biasing. Here P section is connected to negative terminal of the battery and N section to the positive terminal of the battery. Here P section is kept at a lower potential compared to the N section. These are the two types of biasing. And we will discuss what will happen during this forward biasing and reverse biasing. Okay. Now for forward biasing, I'm just writing a subheading, forward biasing. So you take a diode, PN junction diode. So here there is at the central region, there is depletion layer. P section, N section. Okay. This is a depletion layer. Here there is potential barrier. Now P section is connected to positive terminal of the battery. N section connected to negative terminal. This is forward biasing. Now you remember here the direction of external potential is I take it as V. See, applied potential V. Its direction is from left to right. And you see at the junction, PN junction, direction of that electric field, the junction potential, that is also known as barrier potential, is opposite to that of external bias. This you have to remember. Now, what happens during this forward bias? You can see there are holes in the P section. Majority carriers are holes. Here electrons. N section electrons are the majority carriers. Here what happens is this positive terminal repels the holes towards the junction. So the holes reach the junction and it neutralizes some of the ionized cores. At the junction, you can see some of the negatively charged ionized cores at the depletion region. It neutralizes some of these cores. And then they cross and they are attracted by the negative terminal of the battery. Negative attract that holes, positive. Negative is fond of positive. It will be attracting the holes. So we can see the width, that negatively charged core region is reduced. In the same way, this negative terminal repels the electrons towards the junction. These electrons neutralize some of the holes, ionized cores there, ionized cores, neutralize. And then they are attracted by the positive terminal. So what happens at the junction? You know, some of the ionized cores are neutralized. So width of the depletion layer will decrease. So during forward bias, width of the depletion layer will decrease. Okay. And the width of the depletion region is a measure of resistance of the diode. When the width of the depletion layer decreases, diode resistance decrease. So it will offer negligible resistance to the flow of current. Okay, so diffusion become very easy then. Diode offers a very small resistance to the flow of current. The current is called forward current. It is of the order of milliamperes. So during forward bias, what is happening? What is happening to the depletion layer? Thickness of the depletion layer decreases. Okay. Thickness of the depletion layer decreases. So when thickness of the depletion layer decreases, resistance of the diode decreases. And third point is, you see the net potential at the junction. At the junction, you know, applied potential V and barrier potential are opposite direction. So effective potential at the junction decreases. Okay. The applied potential, that is due to the battery, opposes the barrier potential. Okay. So if V0 is the barrier potential and V is the applied potential, V0 applied potential, sorry, V0 barrier potential. V applied potential. Then net potential at the junction. Is V0 minus V. So we have seen applied potential and the junction potential are in opposite direction. So net potential at the junction is V0 minus V. The potential difference across the junction we also call as barrier height. So when you apply forward bias, what happens? The barrier height decreases, net potential decreases. So during forward bias, what will happen to barrier height? Decreases. What is barrier height? The potential difference across the junction is known as barrier height. Okay, due to forward biasing, the barrier height decreases. So due to forward biasing, barrier height decreases. So we can represent with a diagram. See, we represent barrier height in this way. This barrier height, this potential difference, we represent by V0. Potential difference between P and N junctions. Here no bias is applied. Now with the bias, when you apply a forward bias, the potential difference will be decreasing, this one. This is effective potential that at the junction V0 minus V with the forward bias. Okay, with the forward bias. So children, so during forward bias, what all things happens? What are the main points to remember? P section of the diode is connected to the positive terminal. N section of the diode is connected to the negative terminal. Okay. Width of the depletion layer decreases. Width of the depletion layer is a measure of the resistance of the diode. So the diode offers a very small resistance. Effective potential at the junction, barrier height, it decreases. Forward current is of the order of milliamperes. But when we apply forward bias, the diode will conduct when the external potential difference is above than the barrier potential. Barrier potential is 0.3 volt for silicon semiconductor and 0.7 volt for germanium semiconductor. So diode will conduct only after this 0.3 volt or 0.6 volt, depending on the semiconductor diode. After that 0.3 volt, the current will be very large. Okay. So when we apply more and more potential difference across the junction, the potential width of the depletion layer decreases and resistance decreases. As we give more forward voltage, depletion layer become almost zero. So then there won't be any resistance for the current, for the diffusion of current, the charge carriers. But you have to remember current is of the order of milliampere. The forward current is of the order of milliamperes. This is about forward bias. Now we will discuss reverse bias. In reverse biasing, P section of the diode is connected to negative terminal and N section connected to the positive terminal of the battery. Let us see what happens during this reverse bias. See, this is the PN junction diode. PN junction here. P section, N section. So P section is connected to negative terminal. And N section is connected to positive terminal of the battery. And you know, P section holds, majority carriers holds. N section electrons. And few holes will be there, you know, minority carriers. Here P section, few electrons. Here what happens is, see this negative terminal attract the holes towards it. So what will happen? The holes move away from the junction. So you know here the ionized cores, number of ionized cores increases because electron hole lost means negative charge. Similarly, the positive terminal attracts the electrons away from the junction. So at the junction, the negative, the positively charged core increase. So what will happen? The width of the depletion layer increase. So this width of the depletion layer become more. If width of the depletion layer increase, resistance will increase. Resistance of the diode will increase. Practically no current flows through the diode under reverse bias. However, you know, there is a small number of minority carriers in both the N and P sections. These minority carriers cross the junction because in P section electrons are minority carriers. They will be attracted by the positive terminal, or they will be attracted towards the positive N side. Similarly, holes of the N section, holes minority carriers will be attracted by negative terminal here. So due to the movement of this negative minority carriers, there is a small current. That current is known as reverse current. That is negligible. The reverse current is very small. Practically, diode will not conduct, but however, there is a very, very feeble current due to minority carriers. That is known as reverse current. It is of the order of microamperes. And you see the potential at the junction. See, applied potential direction is in this way. You know, potential difference direction from positive to negative. See, this is a direction of applied potential. You come to the junction. Here it is negative and positive. See, both are in the same direction, right? So applied potential aids the junction potential. So effective potential at the junction is V0 plus V. What is V0? Potential barrier. V, applied potential difference. Barrier height increases. Okay. So this is what happening in reverse bias. So what happens? I will write as points. Negative terminal of the battery attracts the holes towards it. Positive terminal of the battery attract the electrons towards it. So width of the potential barrier, depletion region increases. Width of the depletion region. So resistance offered by the diode increases. So since both the charge carriers move away from the junction, width of the depletion region increases. More width of the depletion region, more resistance. Diode resistance offered by the diode increases. Okay. The diode will not conduct practically. Now barrier height increases. The net potential difference across the junction is net PD across the junction is V0 plus V. Barrier height increases. But due to the minority carriers, there is a reverse current. Due to the flow of minority carriers. There is a negligible current. Called reverse current. The reverse current. The reverse current is very small. It is of the order of microamperes. Microamperes. Then we can represent the barrier height. So here, due to reverse biasing, barrier height increases. See, this is the barrier height, junction potential V0 without bias. And this is with bias. This will be V0 plus V. So this is about biasing of a semiconductor diode. So I will give you a quick recap. What is a diode? A diode is a PN junction provided with the metal contacts. And we need to bias diode for conduction. Why we need to bias? Because of the junction barrier, potential barrier. There are two types of biasing, forward biasing and reverse biasing. In forward biasing, P section connected to the positive terminal, P to positive terminal of the battery, N section to the negative terminal of the battery. During forward biasing, width of the potential layer decreases, barrier height decreases, current is of the order of milliamperes. Diode offers a very small resistance. When you forward bias increases, applied voltage increases, the resistance becomes negligible. Now reverse biasing. P section of the diode is connected to the negative terminal and N section to the positive terminal. Since both the charge carriers move away from the junction, width of the depletion layer increases. Resistance of the diode become very large. Practically, it is not conducting. However, there are some minority carriers in both P and N sections. They move under the junction field. They constitute a small current of the order of microamperes. This current is known as reverse current. During reverse bias, width of the depletion layer increases and barrier height increases. Applied potential aids the junction potential. Net potential at the junction is V0 plus V. What is V? V is the applied potential difference. This is about reverse bias. Okay, children? So we will continue in the next lesson. Thank you for watching.